Okay, the session is now recorded. Okay, so let me have a brief recap. We are solving this question here, question 1 of the first tutorial sheet about this contraption. We have a 15 kilogram block or load of bricks, a pulley, frictionless, massless pulley, and a 28 kilogram counterweight. We want to know what's the acceleration of the load of bricks and what's the tension in the rope, basically, and then we wanted to do some comparisons. So what I did is I started by first of all drawing everything. So this is a pin that supports the pulley, and then we have the load of bricks M1 and the counterweight M2. And the other thing that I did is I started, so I am isolating M1 to draw the free body diagram of body 1, and I'm isolating M2 to draw the free body diagram of body 2. Now, I was saying, how many forces are acting on body 2? While I draw it, please tell me. How many? 2. So I will call this T2 and M2G, of course. So we have the weight of the mass and you have the tension of the rope. Now, I call them T1 and T2, but since the pulley is massless and frictionless, okay, we know, or you can demonstrate that these T1 and T2 are the same T. Okay, how do you go about that? Well, if I pull this down and I do the free body diagram of the pulley, okay, what happens is that on this side, I have T1. On this side, I have T2, that they are, of course, equal and opposite to each other, here and here, for Newton's third law. But T1 and T2 are the same, because remember, this is completely in equilibrium, because it has no mass. The sum of moments is I alpha. Remember, sum of moments is equal to I times alpha. Alpha might not be 0, but I is 0. What is I? What is I? Remember when I say sum of moments about G equals IG times alpha? What is IG? Come on. Mass moment of inertia. Mass moment of inertia. What is the mass moment of inertia of a thin disk? A pulley is like a thin disk. This is, okay, half mr squared. So if the pulley is massless, so if the pulley has no mass, the sum of moments is 0. Do you agree? Even if it's moving, even if it's accelerating, still 0. So that means that the moment of T1 times the radius must be equal to the moment of T2 times the radius. But T1 times R equal T2 times R and R go away. That means T1 is equal to T2. So let's forget about these numbers. Let's call everything T, and that's it. Okay? Now, it looks like I'm skipping steps, but you should always do this kind of check every time. Okay? Okay, the important part is here anyway. So this is the free body diagram of mass 1. This is the free body diagram of mass 2. Right? So let's do equilibrium equations. What are the equilibrium equations? How is a body in equilibrium? If the sum of forces is 0. Now, in this case, do we have acceleration or not? What do you think? You have a 15 kilogram block on one side and a 28 on the other side. So what would happen? Well, of course, okay, I'm expecting that the counterweight will pull down and the load of bricks will go up. We'll have to make this formal with the kinematics assessment as well. Remember, if you have two bodies, each one has got its own free body diagram, but you also have a kinematic relationship between the two. So in this case, we need sum of forces equals mass times acceleration, and sum of moments equals IG times alpha. Now, these loads are not rotating by any means, so we can forget about the sum of moments, but the sum of forces equals to mass times acceleration. Again, there are no horizontal forces, so I will not even bother writing the sum of forces along x equal to mass times acceleration along x, because, so let me write them down here. So the three equilibrium equations are sum of forces along x equals mass times acceleration along x. Sum of forces along y is mass times acceleration along y. Sum of moments around g is ig times alpha. Remember this? Oh, sorry, can't see it. There you go. Yes, these. Okay, remember these? These three is what we used 40, 25 last year to go about all the exercises, really. Now, this one is useless because none of these is rotating. So, of course, there are no moments. See, all the forces are passing through the center of gravity. So there is no moment. So 0 equals 0, useless. There are no horizontal forces. So again, no forces, no acceleration, 0 equals 0, useless. The only equation that is useful is this one. So let's use this equation for both masses. But one thing I missed is reference system, okay? Because I didn't tell you which one is x, which one is y. I'm assuming that you know. But let's make it clear. Let's make it clear that this is the y-axis of body 1, and this is the y-axis of body 2. Okay, you can choose different axes. Doesn't matter, because everything will be clear once you state explicitly the kinematic relationship that makes that gives you a relationship between these two coordinate systems. Okay, so let's do sum of forces along y for body 1. So let's do this equation 1. Is plus t minus m1g equals the mass of body 1 times the acceleration of body 1 in the y direction. Okay, so this is in the y direction, but I won't bother writing it because it's only an acceleration in the y direction. Okay, so let's just call it A1. Right? Good. Can you tell me equation 2? Come on, equation 2. T minus equals. Correct. Okay, so let's check. So this is a system of equations. Let's check how many unknowns we have. So we have T is my first unknown. The masses are given. So A1 is my second unknown, and A2 is my third unknown. Okay, because of course, one body will be accelerating in a certain way, the other body will be accelerating in a different way. Or will it? We don't know yet. We will know once we state explicitly the kinematic relationship between these two. Because these are now free body diagrams, means this can go anywhere. They are just under the influence of those forces. They are not connected to each other in this configuration here. See, they are completely disconnected. But we know that they are connected. So what is the kinematic relationship here? Well, let's look at the actual rope around it. We know that if mass 1 goes up by 1 meter, what happens to mass 2? It goes down 1 meter. Okay? So we can say that the displacement of mass 1 is equal and opposite to the displacement of mass 2. Agreed? If one goes up, the other goes down by the same amount. So kinematic relationship. Mass 1. The kinematic relationship says that the displacement of 1 equals and opposite to the displacement of 2. Do you agree with this? S1, displacement of 1 is equal but opposite to the displacement of 2. Sir? Yes?
How come it's not? The sequel equation, how come it's not MTG minus 2? MT is everything at once, so it shouldn't be going down like that.
You don't know that yet. Okay, so the student here in the class is asking, why is this one positive and not negative? Well, first of all, because Newton's second law says the sum of forces is m times a. That's it. Now, if the sum of forces is negative, the acceleration will be negative. Fact is, you can't state that in advance. Although you know it, you should stick to the rule, because then the sign, after you found it, the sign will tell you if it's going up or down. Okay, so don't mess with the equation beforehand, because when you solve it, then you might get the wrong sign and you might misinterpret the result. Okay, just stick to the rule. So this is S1 equals minus S2, but this is not helpful. So how does this help with this equation? What's missing? What is the link between displacement and acceleration? Come on. So what you have to do is differentiate twice, because it's true that S1 is equal to minus S2, but if I take the derivative of this equation once, I get the velocity of 1 equals minus velocity of 2. And if I differentiate it one more time, I get A1 equals minus A2. Agreed with me? And then there you go, my third equation that helps me solve these three unknowns. Okay, so let's differentiate once, we get V1 equals minus V2, and differentiate it one more time. Let me rearrange this, sorry, because I don't like this. So let me do this here. So you differentiate this one and you differentiate this one more time, differentiation. You get A1 equals minus A2. And there you go. This is my third and the third equation, because this third equation here contains my second unknown and my third unknown. Okay. Now you solve a system of three equations and three unknowns. This is very easy to solve. And we got back to your question. Okay, look at it now. If I plug equation 3 into equation 2, what happens is that A2 is minus A1. Okay, and that is your original equation that you wanted me to write, which is correct, but formally you're skipping a step. Okay, which is easy now. Okay, we are skipping a step because it's a very easy problem. But if you have a very complicated mechanism with many interconnected bodies, might not be as easy to say, oh, this acceleration is equal to who knows. Okay, so you have to make sure you follow the kinematic chain, that's called, and you're going to be dealing a lot with the kinematic chains when you do mechanisms, velocity diagrams, acceleration diagrams, all fun. Okay, I won't bother solving this, but can you please solve it for me? You have 10 minutes. Okay, I'll give you 5. 5 minutes, solve 3 equations in 3 unknown. And actually, this is a 2 equation into unknown, because this equation, if you plug this here, it becomes much easier. You know what? I'll show you how I do it by hand. So if I plug 3 into 2, I get that T minus M to G equals minus M to A1. Do you agree? Now, if I sum this equation to 1, what happens? Let's say if I subtract this equation from 1. If I subtract this equation from 1, so I do 1 minus this, equation 1 minus this, t and t go away, easy. This one becomes m2 minus m1 times g. So I was saying this minus this, so t minus t go away. This minus this becomes m2 minus m1 times g. And this minus this becomes m1 plus m2 times a1 equal m1 plus m2 times a1. Ah, come on. And lo and behold, we can already find a1. So a1 was my second unknown. So this unknown t was annihilated, and it must be annihilated. Why? Look at this. T is an internal force of the system. Internal forces always equal and opposite to each other, always destroy each other. So you can always write an equation that doesn't contain any internal forces. So this is the equation of the entire system. And now I can find a1, therefore a1 equals, look how beautiful is this, m2 minus m1 over m1 plus m2 times g. So this is an acceleration. This is kilograms over kilograms, so they go away. So acceleration equals acceleration. And see now what I was saying, leave, don't put numbers in, because now look how beautiful is this. We can make all sort of, we can play all sort of games with this. What happens is if M1 is the same as M2, what happens if the counterweight is the same weight as the load of bricks? See, M2 minus M1 goes to 0. The acceleration becomes 0. In fact, it doesn't move. That's it. All right? Aren't you excited? I think it's so beautiful. Is it not? And you have the tools to appreciate this, which not always, well, not everyone has. If you were now majoring in English, you couldn't appreciate this. You now can. I think that's beautiful. All right, well, we spent a lot of time over this simple problem, but I wanted to make sure we pinpoint all the basics. Any questions? Also online, students, yes. Second, use G. 9.81, yes. So G, here I was asked a question, G is always 9.81, it's fine. Don't use 10, use 9.81 meters per second squared. Always remember your units. Actually, there are numbers here, so please put numbers. So how much is this in meters per second squared? Second, 2.96, which is much smaller than 9.81 meters per second squared, and makes sense because we have a counterweight. Okay, so the counterweight is slowing things down. Because if there was no counterweight, what happens if the mass of the counterweight is 0, m2? If m2 is 0, A is equal to G, free falling. Okay, it works, checks out everything. Nice. I think that this problem had 2 more questions. Let me check those ones. What is the tension in the rope? Well, that's very easy now. You either look at equation 1. Now that A1 is given, A1 is a number, everything is a number. Here you can find T. T is just this plus M1G. That's it. Yes. How did I get from here to here? Oh, S1. It's differentiation. So you do the derivative of the, you have to remember, derivative of the displacement is velocity, derivative of velocity is acceleration. Now, since this is an equation, whatever you do on the left side, you do on the right side, and it's still an equation, okay? Even if you do very complicated things to an equation, it still remains an equation. That's the beauty of it. All right, this was part A. Part B asks, what is T? Well, I can say that T equals M1G, so M1A1 plus M1G. But T is also equal to, if I take equation 2, T is also equal to minus, M2G minus M2A1. Yes. Okay, so what is the relationship? If you find these numbers in newtons, of course, can you tell me what these numbers are? So this is the same number, so it doesn't matter. This should be the same number because it's T. T is the same. You either take T from equation 1 or from equation 2, it doesn't matter. And you can check what is T with respect to what? Oh, to the weight. So part C is basically asking you, what is T? Is T greater or smaller than M1G? And is T greater or smaller than M2G? Okay, and you can ask these questions. You can answer this question by checking how much is T and how much is MG. Of course, you can see that T is greater than M1G because there is this thing added on top of it. And T is smaller than M2G because M2G minus this. Okay? Very easy, without even using numbers. But you can put numbers, and you are encouraged to use numbers at the end, also because at the exam, that's what you're going to do anyway. All right, let's do directly problem number 5 on this same sheet, which is much more complicated. And I ask you, how many free body diagrams we need here and how many kinematic relationships? While I draw this on the screen. So how many free body diagrams? Online students, how many free body diagrams? Come on, answer me. How many online students we have? 70. Amrit is saying 3. Do you all agree? Yeah, Marius also says 3. So we have a block A. I know I'm not showing the notepad because I need it. I need this. So I'm drawing it, but I need this. I need this on top. Otherwise, I can't see it. So bear with me for a moment while I draw this. Now we have a pulley. Yeah. This rope, I'll draw this. Let's use this. And we have another pulley here. And let's color code it as well. We have this is, so this is red. No, this is blue. This is red. And this is green. All right. So we have blocks A, B, and C placed as in figure and connected by ropes of negligible mass. That makes our lives much easier, because if you have to account for the mass of the rope while it's being pulled, that also is subject to acceleration. The rope can clamp up. Okay, so saying that it's massless makes it very easy. Both A and B weigh 25 newtons each. So it's not given the mass, it's given the weight directly. And the coefficient of kinematic friction between each block and the surface is 0.35. Block C descend with constant velocity. Now this is very important. Okay, make sure. What does it mean, descending with constant speed? Second, sorry. No acceleration, correct. So remember, acceleration is the derivative of velocity. If the velocity doesn't change, the derivative of a constant is 0. All right, so put this in the bag. We're going to use it very soon. And yes, Mahmoud is, online is also correct. There is no net force on the body because the sum of forces is 0, must be 0, because then there is no acceleration. That's exactly the same thing. Find the tension in the rope connecting blocks A and B, and what is the weight of block C? And if the rope connecting A and B were cut, what would be the acceleration of C? This looks like one of the exams I'll give to the first years this time around. Looks nice. Yeah? No, I won't say it again. Let's start. So how many free body diagrams? You said 3. Let's do these 3 free body diagrams. How many forces are acting on block A? Come on. 4. Can you enumerate them for me? The weight, of course. Normal force.
I can't see what you're drawing.
Oh, sorry. This is one thing that I have to get used to it. So WA. So WA is the weight of A, the normal force on A, you were saying. Then what? The tension of the rope. Let's call this T1. Now see, is this T1 all along? No. Why not? Because there's block B in between. Okay. So imagine if this rope had mass, the tension in the rope is not the same everywhere. See, imagine that B is part of the rope. Just the fact that this B has mass, it doesn't mean that the tension is the same everywhere. So let's call this T1 because this tension here will be called T2. What else? There's a friction. Where is friction applied? At the interface between the block and the ground, and is going in a different direction. How much is friction force? Can you remind me what's the definition of a friction force? Mu K times M. Okay, right. So let's put this highlighted to say this is recall. This is old knowledge that you should already have. All right, we have 4 forces here. Do you want to start analyzing this and then do the free body diagrams of all the other, or do you want to do the free body diagrams first and then all the equations? Your choice. Come on. Free bodies first. So let's do the free body diagram of B, which looks like this. Oh, what am I missing here? The system, coordinate system. Let's call this YA, and let's call this XA. So for B, which looks like this, how many forces are acting on B? 5. Can you enumerate them for me, please? So let's start with the weight, of course. Weight of B. What else? Normal force. Which direction? Come on. Can you tell me in words which direction? That's a very good way of stating that. So perpendicular to the ground. That's why it's called normal force. It's normal to the ground. So perpendicular to the ground, that's NB. What else? Tension 1 and tension 2, correct. Also, I'm read online, also correct. So tension, this is T1 and this is T2. Again, tension 1 must be going opposite, must be in contrast with this tension 1. So we kind of know the direction of this. We are not sure about the direction of this, but of course it's going to be this way anyway. But it's pulling. They're both tugging on body B. But one will be greater, so body B will follow that one. Is that it? 1, 2, 3, 4. You said 5. What's missing? Friction. Which direction? Parallel to the ground. Yeah. And this one is friction force B. All right, let's do C. So for C, how many forces are acting on C? 2. And those are the weight of C, which we don't know, and the tension. Which tension? T2, correct. Okay, very easy. What's missing here? Here we are missing the reference, the coordinate system. How would you choose the coordinate system here? Yes, so you want to align it so you don't have to split all vectors ever. You have 5 vectors and they are all mostly perpendicular to each other. Okay, so if I use this reference system, XB and YB, I don't have to split any of the vector but WB. See, because WB is neither parallel nor perpendicular to the ground. All the other forces are parallel or perpendicular to the ground. So the smart choice, which is not the only right choice, okay, you can choose whatever you want, but it's the smart choice that you only split WB into components rather than every other vector. Okay, it's the engineering choice. And of course, for this one, we only need, let's say, Y. We don't need the x-axis, everything is horizontal. And I am being a bit provocative here. I'm not using the y-axis upward, I'm using it downwards. Why? Reasons. Because it's the same. I want to show you it works even if you choose an odd, even if you have an odd choice of axes. Because everything boils down to the kinematic relationships. If you use the kinematic relationships in a good way, it doesn't matter what you use, always checks out. Okay? Right. So let's go on to the actual mathematics. So the physics part is done. Now we do the mathematics part. So let's start with body A. Body A has got 2 equations that we have to take care about. So first of all, do we need sum of moments anywhere? So let's look at body A. Body A, all forces are passing through A? No, they are not. The friction is not passing through the center of gravity, of course, because it's happening at the ground. So what's going on there? Does it mean that body A is rotating? Well, it will try to rotate, of course. If you pull anything, it tries to topple down. Okay, so if you pull it, it topples. But what happens is that this normal force that I have drawn here, I really should have drawn this here. Okay. So yes, it's true that this friction force tries to topple A in this direction, but then, oh, my fault. So this is in this other way, okay? It's true that this friction force tries to topple A in this direction, but this normal force pulls it back. So there is the sum of moments, but it's just saying, okay, the normal force is offset that much that is required for A to not topple over. Of course, if you pull a lot, at some point, the normal force will reach this point here. And once it's here, it can't be offset anymore. And then at that point, you get toppling. I mean, this is not the case, so let's forget about this. This is also happening for NB. In reality, this normal force is a bit here. Okay. So let's neglect some of moments. We know that normal force would be shifted a bit to make up for the fact that the friction force is not applied to the center of mass, but it doesn't matter. So let's do sum of forces along X and along Y. So the sum of forces along X is T1 positive along XA. So T1 and XA share the same coordinate system. And FFA, which you taught me earlier, is minus mu k times n, in this case NA. That's it, equals mass of A times the acceleration of A. The acceleration of A along X. So this is the X acceleration of A. Don't like it. Let's do it like this. What about in the y-axis? Well, in the y-axis, we know that this is not going anywhere. This is staying at the same quota, at the same height for the entire process. That means there is no speed, and that means in the vertical direction, and that means there is no acceleration in the vertical direction. So we can just say that WA equals NA. Well, let's write the equation. NA minus WA equal to 0. So that means that this NA is WA. Okay. That's it. That's all we can say about body A. Let's append two more equations for body B. X and Y. So this is X and Y. This is X and Y. But now for body B. So can you tell me what's the equation along the x-axis for body B? Sum of forces equals mass of B times acceleration of B along the x-axis. Its own x-axis. Come on, T2 minus T1. What else? Minus the friction force, which is minus mu k, the normal force on B. Agreed? Good. That's it? No. What's left? WB. All WB? No. So how do we do that? We have to split this into components. So one component must be along this axis. So I'll do one component parallel to this, and one component is parallel to this. Okay? So that means this component here is WBY, and this component here is WBX. Now let me draw this here. This is WB. This is 90 degrees. So WB is the hypotenuse of this triangle. All right? Okay, we want to find the edges of this triangle, WBY and WBX, given what we are given here. Which angle is given? Let's check. So we know this angle here is, 37 degrees. That's an odd choice of angle. 37 degrees. So if this is 37 degrees, this angle here, this one, where is 37 degrees here? Is it this one or this one? It can't be this because it's 90 degrees. It's either of the two.
And the lower angle.
So let's check. So this is the weight. This is 37. So the horizontal line and this line make 37. So if we take the perpendicular to the horizontal line and the perpendicular to the ground, they also make 37 because I'm just rotating the angle 90 degrees, okay? So the perpendicular to edge 1 and the perpendicular to edge 2 make the same angle, okay? Yes, okay, yes, I'll give you a break now, don't worry. And so let's do this. This is 37. So you tell me now, how much is the WBX? How do you find this? Is this opposite or adjacent? Opposite. So WBX equals WB times sine of 37. Okay. So it's minus because see, this component is opposite to X. So it's pulling down. So minus WB cosine 37. And that's equal to mass of B times the acceleration of B on the x-axis. Okay. And sorry, let me change this one as well because it was. Okay. Alongside this one, we have that plus NB minus WBY. That's it. We only have that one. So we have that NB minus WB. Did I say cosine? It should be sine. Sorry. Thank you for not telling me. So cosine of 37 equals 0. All right. So we also know that this NB here, we can just take it out from this, which is a number. We know WB is 25 newtons. So this is a number. This is a number. Okay. And let's do C. Well, C is very easy. We only need one equation for C, which is along Y. What's the equation? What's the equation? So WC minus T2, because I'm using this weird thing, okay? Yes? No. Well, no, it's not possible. See, Y is perpendicular to T2 and T1, so they have no component along Y. It's this Y, okay? This is the Y of body B. And we have chosen that Y so that all these other forces along the ground don't have any component along Y, okay? No, it doesn't. How? It's completely along X. It's parallel to this, okay? Okay, so for C, I said WC minus T2 equals 0. And this equation is like that because we have chosen this reference system. So WC is positive, T2 is negative. Okay, let's count unknowns. T1 is my first unknown. Now, NA is not unknown. NA is WA. This is a number. Okay, so I will not, let me not count these 7 equations in 7 unknowns. Okay, I will just skip the things that we know already. So NA is not an unknown. This one is unknown. Also, MA is not unknown because MA is WA divided by G. Okay, although it's not given the mass, but we know it's W divided by G. This one is useless because, well, we used it here. This one, we have T1. T1 is my first unknown. T2 is my third unknown. And then we have NB is this. So NB is given here. It's a number, so I don't use it. WB is given. And ABX is my fourth unknown. 1, 2, 3, 4. What's left? WC is my fifth unknown. So 1, 2, 3, 4, 5. And T2 is my third, 1, 2, 3. So this is equation 1. This is equation 2. This is equation 3. We have 3 equations and 5 unknowns. Ouch. Or if you want, you have 5 equations and 7 unknowns if you take NA as unknown. So we are 2 equations short. We are 2 equations short. Where do we find them? What's missing? I told you, these are the forces. So this is the kinetics. What's missing is the kinematics relationship, okay? So what is the kinematic relationship between A and B and C? That's 2 equations. So if I move A this way, so let's move it along its own axis, okay? If I move A along its positive x-axis 1 meter, what happens to B? Well, it moves up 1 meter, okay? But along its own x-axis. It's 1 meter along its own x-axis. All right, good. And what happens if I move B 1 meter along its own x-axis? Well, C moves down 1 meter along its own y-axis. Okay, so the first kinematic relationship says that the displacement of A along its own x-axis equals the displacement of B along its own x-axis. The second relationship says that the displacement of B along its own x-axis equals the displacement of C along its own y-axis. All right, and these are all positive. Now we do, but these are still unknown. So our unknowns are A and AX and ABX. So we have to make sure that we can differentiate it once here, differentiate this, we get the velocity of A in X is the same as the velocity of B in X. And differentiate it one more time, the acceleration of A in X equals the acceleration of A of B in X. And I do the same for this and this. The velocity of Bx equals the velocity of Cy. And the acceleration of Bx is the acceleration of Cy. That we know that this one is 0, because we know that this one is constant. Okay, remember this is what we said earlier, that C is descending at constant speed. So if this is 0, so this one is equation 4, and this is equation 5. And there you go, you can solve 5 equations in 5 unknowns. We know that this one is this, which is 0. So you can solve now equation 2. And then you go here and you say that also this is 0. And then you solve equation 4. Sorry, equation 1. Okay. I see there is some confusion about the negative displacement of C along its y. No, it's negative displacement if you've chosen the other axis. If you've chosen y upwards, this would have changed the kinematic relationship here, but it's fine. It's still 0, doesn't matter. Okay, 12:03. Any questions on this? If not, I'll give you a break, 10 minutes. Okay. All right, online students, online. So I'll see you back at 12:15. Okay, and we are going to start with the new stuff with balancing of rotating masses. All right, no questions? Enjoy. Second? Oh, yes. Thank you. So I'm going to pause the recording, but you also remind me to restart the recording again. So I'll pause recording now, and I'll see you later. 10 minutes. Okay, we are recording again. As I was saying, we are now doing the balancing in one plane. Guys, Please, eyes on me. Cheers. Which is this one. So two masses revolve together in the same plane at an angular distance 45 degrees apart. The first is a 3 kilogram mass at a radius of 225 millimeters. The second is a 5 kilogram mass at 175 millimeters radius. Calculate the out of balance force that's happening at two. Yes, it's been recorded, Lynn. Thank you. Where is Lynn? Can't see it. She's no. Okay. And all of this is happening at 2 revolutions per second, 2 RPS. And also the position of a 10 kilogram balance mass required to reduce this unbalanced force to 0. Now, let's recap very briefly what's happening when you have, let's say, a shaft that feels an unbalance. So let's say you have this one. So this goes around and round at a certain speed omega, angular velocity. You can't see this. Let me put this on. Yes. Let me put this larger. Okay, what's happening here if you have this going around at an angular speed omega is that this, of course, if you remember what happens to this is following a curved path. So if you recall curvilinear translation, which is what this particle is doing, it feels two accelerations, tangential acceleration, normal acceleration. Now, if omega is constant, remember there is no tangential acceleration. Remember, tangential acceleration is omega dot r. Let's call this r. This distance is r. And the normal acceleration is, how much is that? Come on. What's the normal acceleration? Omega squared times r, or v squared divided by r. Guys, revision, okay? This is what we did last year, yes. Yeah, tangential acceleration is this one. This W is on this is angular velocity. Okay, and alpha, so W dot is alpha, it's the angular acceleration. Remember? We called it last year, we called this alpha. Now it's better if we start calling it omega dot. So you also know where it comes from, this alpha. It's the same thing. Now, omega is constant, so this one is always 0 because a shaft is rotating at constant speed. So there is no tangential acceleration, but there is a normal acceleration. Normal acceleration gives rise to an inertial force. That inertial force is what we call centrifugal force. The centrifugal force is equal to the mass of the particle. This mass, this particle has a certain mass times the normal acceleration. So the centrifugal force is mass times omega squared times r. Okay? And look at this. If this is going round and round it goes, the free body diagram of this link is this, and of course, the reaction force of the pin, which is also equal to Fc, because everything must be, everything is going at constant speed, so everything is rotating. Now, this pin feels a force that is rotating. If this pin is not completely fixed to the ground, this pin will start wobbling. Okay, this wobbles up and down, and left and right. As this rotates around, it's not good for the basement. If you have an engine, the engine mounts will start vibrating if the engine is unbalanced. Okay, that's the idea. Okay, so the sum of forces is equal to 0 because we say everything is going at constant speed. So the sum of forces is equal to the sum of mi omega squared Ri. So every mass, you might have multiple masses sitting at multiple radii, but all at the same constant speed. So omega is the same. So ideally, I can take omega out. So this is equal to 0, okay? And if I take omega squared out of the sum, I get that omega squared sum of mi Ri equal to 0. And then I can divide everything by omega squared. And this is the equation I need. This equation here is what you did with Faris. This is the so-called MR diagram. It's not an MR, it's just the sum of forces. You call it MR diagram just because omega squared is common, so you take it away. That's it. So there is no fancy MR diagram anywhere. It's just sum of forces. And these are the same vectors, but are much shorter because you have got rid of this omega squared scale factor. Okay, so last reminder before we start. What is the sum of forces? How does it look like graphically? The sum of forces equal to 0. If I have a vector and a vector and a vector and a vector, is this sum of vectors equal to 0? No. Why? What's the sum of these vectors? The sum of these vectors is this. Okay? This is the sum. So in order to make this sum equal to 0, we must add another vector here. And now there is no sum here. They start and end in the same place. And so now this polygon is closed. The sum of these vectors, sum equals 0. All right? This is the whole idea. You have masses. Each mass has its own force. Its own force has got a certain direction and length. You sum all forces. If they don't close up, there is imbalance. So if the polygon doesn't close up, there is a reaction force at the pin that must balance it. But that balancing force at the pin is shaking everything else around it. So in order to make the pin not react with any force that is rotating, you need to balance it on the shaft itself. So let's go about here. Now, you know what? Let me take this, but just shrink it down here. There you go. Nice. So you have it for reference. Now let's start with question 1. So problem 1. Problem 1. While I draw it, you can read it, because I need to read it as well. We have two masses, and they are at 45 degrees apart. It doesn't tell you where are the masses, because they can rotate anyway. You just know that they are relative to each other, 45 degrees apart. So I will say that mass 1 is at 0, and mass 2 is at 45. Doesn't matter. It doesn't change anything. All right. The first mass is 3 kilograms. So you know what? I'll show you. The easy way of tackling these problems is to create a table. And I'm sure that Faris has told you about the MR table. Did he give you the table? Probably, yes. So the table is identification of the body, the mass of the body, the radius, so the mass of the imbalance, the radius at which this imbalance sits, the angle of the imbalance, so also MR, the multiplication of these two, and the angle at which this imbalance sits. Right? This is a table. And we have mass 1 is a 5 kilogram mass. Sorry. Mass 1 is a 3 kilogram mass at 225 millimeters. And at 0 degrees, I said, because this is my reference. And mass 2 is a 5 kilogram mass at 175 millimeters radius and at 45 degrees relative to mass 1. Okay, we also have a third mass, which is our balancing mass, which is 10 kilograms at a radius that we don't know. I'll call it R3. And it must balance everything. So we don't know theta, so let's say theta 3. So this is what I wrote down. Okay, so body 1, so mass 1, it's a 3 kilo also. Let's put here, very important, units. This is kilograms, this is millimeters. So what are the units of MR? Kilogram millimeters. Yes. No, you don't need to change it 2 meters. There is no requirement. It's fine. Let me see if I can. Oh, calculator. There you go. So let's do 3 times 225. This is 675. And 5 times 175. This is 875. Kilogram millimeters, of course. Now, this one, of course, is 10 R3 that we don't know. Okay, that's the multiplication between 10 and R3. So look, we have 2 unknowns, R3 and theta 3. But it looks like we only have one equation. The sum of forces equal to 0. Why do we have 2 unknowns and one equation? Yes, so what you're saying in proper words is we have a vectorial equation. A vectorial equation can solve for 2 unknowns at the same time, okay? Because you can always split it. So I'm doing this with the graphical method. You at home do it with the analytical method, okay? Which is just splitting the forces in the X and Y and finding what is the X, Y, and so on. And then at the end you find the magnitude of the force and the angle. All right, so let's do this. The first vector is in blue. And it's a 675 millimeters vector. Oh, now we have to choose a scale factor here. If you want to use a graphical method, you need set square, rulers, protractor, and a firm hand as well, because everything must be drawn to scale. Otherwise, it's not a graphical method, it's a sketch. And the sketch doesn't work. So, of course, I'm sketching here because I don't have any of these tools. But ideally, what you will do is MR diagram. Let's do it on the other page. The MR diagram for this. Also, let's put this down here then. So scale. And you can say that 1 millimeter is equal to 1 kilogram millimeter. So 1 millimeter on the page equals 1 kilogram millimeter of MR of this. That means that vector 1 is 675 millimeters long. Okay, which is probably too short. If you want to make it a bit, you don't want a tiny diagram, you want a large diagram enough. So it's up to your eye and your engineering judgment to find a good scale factor. Okay. So let's do this. And this is a 675 millimeters at 0 degrees. So this one is my vector. Okay, this is my vector M1 R1, which is 675 millimeters and also 675 kilogram millimeters. Now we have another vector, which is the green one, which is longer. See, longer. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. So let's do 675. Let's say that it's 1 square. So this is 7 squares. So 675 to me looks like 7 squares. So that means that this one would look like 9 squares, 875. Okay, so this is 875, it's 9 squares. It's about this long, 336, and it's at 45 degrees from here. Remember, point to tail. This is 45 degrees. Do you agree with me? This is 45, it's same rise over run. It's passing through all the diagonals of the squares. So this is 45 degrees for sure. It's longer than this. So that's it. This one is M2R2. And is 875. So what's missing here now is, now, does this give you a balanced shaft or not? You only have two masses on this shaft at 45 degrees from each other. They are rotating. And so this is the resultant force. The unbalanced force is this one. Okay, this is the unbalanced force, the sum of these two. How do we balance this? Well, we take the opposite of the balanced force and you add it onto it, so you close the polygon. So let's balance this. We can balance this with this vector. So this is the balancing vector. And the balancing vector is this one. So that's called this balancing. And so this is, we know that this length is 10R3. Agreed? Because this blue one is 675, this green one is 875, so this red one is 10R3. Agreed? Now that you have this, you know how much is this, you know how much is this, you can measure this. If you've drawn everything to scale correctly, you can just take your ruler, place it on top of it, and measure how many millimeters is this line, and look at your scale factor. How many kilogram millimeters is the MR of that force? Okay, that's it. Yes. You see the original question? Yes. Very good. So we have two masses. The third mass was used for balancing. Okay, that's why I'm saying the first two vectors are actually what's on there, but then we must place a third mass to balance everything out. Yes?
We actually have to use the graphical method.
In the exam, yes. In the exam is explicitly stated you use the graphical method. The analytical method is more accurate, of course. But again, engineering is not just about analytical things, it's also about making sure that, you know, yes. I'm going to show you now. Okay. So let's go back here. And now, can we have the result? Let's look at the result. The result says that 143 times 10. So this should be 1430. Now, if you draw this to scale, this will measure up as 1430 kilogram millimeters. Okay. But now you know that this is also equal to 10R3. So how much is R3? Well, if 10R3 is 1430, then R3 is 1430 divided by 10. Agreed? So R3 so divided by kilograms. Okay, 143 millimeters. See, the units also check out. Okay, units check out as well. Kilogram millimeters divided by kilogram is 143 millimeters. All right. But a question says, what is the unbalanced force? Unbalanced force is in newtons. Okay. Now this is the balancing force. You know that the balanced force is equal and opposite to the balancing force. Do you agree? Because we had to invert the unbalance to correct for the unbalance. So what we do is what is the force? Remember, is omega squared times mr. So the unbalanced force is omega squared m3r3. So this is 1430. And omega squared is omega is 2 RPS. What is 2 RPS? How many radians per second is 1 RPS? 2 pi. So 1 RPS, 1 revolution per second, 1 revolution is 2 pi radians. So omega is equal to 2 RPS, which is equal to 2 times 2 pi radians per second. Oh, yes, so. Okay, 2 times 2 pi radians per second. Agreed with me? Good. Yes? Second? Yes? Yeah. It does, unless Faris says no, but I think it does. If you measure it with your ruler, you'll find out it's 1430 millimeters. Okay. Not yet. Okay. Yes, but it's the analytical method. You've done it already. I mean, it's the sum of forces. You split it into x and y. So, okay. So I'm going to show you. So now this is omega. So you put this here. And here you end up with a force, which is 226 newtons. Second? Yeah. Radians per second. Okay, online students, all okay? You? All fine? Can you understand what I'm doing? Yes, good. All right, what is the analytical method? That's easy. It's the sum of instead of forces, it's the sum of MRs, okay? It's the same thing. So you have the MR along X, MR along Y of mass 1, MR along X, MR of MY of mass 2, and then you have to find the sum of these and take the negative of that. Done. And then you find the angle and the magnitude by taking again the components, okay? If you look actually at example 1 of lecture 1 of 4025 MAA, it's exactly what you need here. Okay, the first lecture of last year. So I think this is covered. All right. Yeah, I mean, what I mean is what you're doing here is you take this is along X. This is the component along X, the component along Y. This is the component along X, the component along Y. And you know that this plus this must be equal to this. And this plus this. So this and this are the same. Okay, just with numbers. And you have to take the cosine of 45 to find this one, sine of 45 to find this one, and so on and so forth. See, it's not hard. Come on. No? Don't lose yourself in a glass of water. All right, let's do question 2. Also, we have to speed up a bit because there's not much left. Question 2 is faceplate of a lathe, equivalent 2 kilograms at 50 millimeters, another 1 kilogram, position respect 0, and the balance. Okay, now it's the same, it's more of the same. It's exactly the same, but now we have 3 masses, 3 unbalanced masses, and 1 balancing one. Okay, so I'm going to fill up the table. So I'm going to copy this table. But now I'm adding a 3rd mass. Sorry, a 4th mass. This is my balancing mass, okay? Now, while I compile this table, you can look at this, and also I need to look at this. So mass 1 is 2 kilograms at 50 millimeters radius. And it says later 0 degrees. Mass 2 is 1 kilogram at 75 millimeters radius, and it's at 30 degrees. Mass 3 is at 4 kilograms at 25 millimeters radius and 75 degrees. Mass 4 is find the balance mass required at 150. So we know that it sits at 150 millimeter radius, mass 4, but we don't know how much is M4 and theta 4. So we still have two unknowns. If you look at the table I produced, we still have two unknowns. So we can solve exactly. But instead of a triangle, now we'll have a polygon with 4 edges. So let me put up my calculator again. This is, well, don't need a calculator for this. This is 100. Don't need a calculator for this. This is 75. Don't need a calculator for this. This is 100 as well. And I don't need a calculator at all. This one is 150 M4. Okay, now I'm going to sketch this because I can't draw 30 degrees angle, 75 degrees angle on this thing. Okay, I can do it on paper, but not on here. So you do it properly. I sketch it. And I'm sketching the first vector is 100. 100 for me is 5 squares. 3 and 2, 5, yeah. Then 75, I'm going to make this 4 squares at 30 degrees. Something like this. And then I'm going to make 100 at 75 degrees. So it's exactly 5 squares, but at 75 degrees, something like this. Come on. There you go. Agreed? Let's make it clear. This is 30 degrees. This is 75 degrees. Okay. And this is 100. This is 100. And this is 75. And this is M2 R2. This is M1 R1. And this is M3 R3. Okay. So what's the balancing mass? I mean, the fourth one, it's unknown, but we know that it balances everything. So what's the fourth vector? How could it be? There you go. Easy peasy. Come on. Oh. There you go. This one is 150 M4. You can measure it now because you have your ruler. So this is a number. And M4 is that number divided by 150. You all agree? All fine? Good. And now what's the angle? Well, you can measure the angle. This is the 0 degrees. So you measure the angle with your protractor. Starting from this, the angle is this one. This is theta 3. Sorry, theta 4. Okay. Starting from 0, the angle, that's one. Or you can measure the other way around, but it's a negative angle. That would be minus something. But try to stay all positive numbers. So you all related, so you're related to the mass that is horizontal. You've chosen to be horizontal, to be 0. Questions? Online students, any questions? Yeah, students, any questions? Nice. You okay?
Yeah.
Good. 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 All good? All good? Hmm? Nice. How is this? Hard? No? No, it's not hard. In fact, it's very easy. Next week, though, next week, you're going to make this a bit more complicated with the moment diagram. So the MRL diagrams, they just require a bigger table. Okay, so it's not too complicated. Don't worry. All right, let's do question 4. So 5. Is it 5? 5. Yeah, I know. I'm going to just start question 5. I'm not solving question 5, but I want to start it. So you have a place to start. We have 3 masses bolted to a faceplate at 5 kilograms at 125, 10 kilograms at 75, 7.5 at 100 millimeters. This mass must be arranged so that the faceplate is in balance. See, now this is different. You don't have a 4th mass. You must place these masses so that everything is balanced. Okay, so how do you do that? You just have to arrange them so that they form a triangle. Okay, so I'll do the table very quickly for question 3. Sorry, question 5. And we have mass 1 at 5 kilograms. Mass 1 is at 5 kilograms and 125 millimeters. Mass 2 is 10 kilograms at 75. And mass 3 is 7.5 at 100. The unknowns, apparently we have 3 unknowns, theta 1, theta 2, theta 3. How is this even possible? So one thing that we are always doing here is that the first mass we can choose as reference to be at 0. Okay, so there you go, solved. You don't have 3 unknowns because one mass, you can always say this is my 0. And then you take theta 2 and theta 3 with respect of that. So this one is 0. And there you go, you can start. This is horizontal. Let's make the calculation here because we might find a surprise. 5 times 125, 625. 10 times 75 is 750. And this is also 750. There you go. Found the Easter egg. What's the Easter egg? It's not the same line. They just have the same length. What is a triangle? What is called a triangle that has two edges that are the same? There you go. You can arrange them in an isosceles. Isosceles, is that what you say? Isosceles. That's so weird. Yes, in this isosceles shape, apparently. So this goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let's do 10. This is 625. And then we have this one. And this one. There you go. No. This is 750. and this is 750. So what are the unknowns? Well, theta 1 is 0, we said. Theta 2 is this. And theta 3 is this. You draw it, you measure it, done. Okay, easy. And again, it might look, oh, we've done it. Yeah, I thought I would start it, but then I got carried away and I solved it. Sorry, I spoiled all the fun. So that's it. You now have 10 minutes to relax and clear out the room. Okay, not you online students, you stay where you are. Thank you very much. Any questions? No questions? No? Online students, any questions? Guys, you know what? I'm going to put this on Aula, okay? I'm putting all these things on Aula so you can revise them.
What would this?
So let me just, okay, guys. Thank you very much for the online court. I will see you next week, same time, same day. Okay. Bye. Every Tuesday, 11 o'clock. Okay, online, same link. Bye bye. See you. Let me stop recording.